Nathan Fitzpatrick from Quantinuum, a framework for spin-adapted quantum simulation of fermions.
Okay. So I'm going to be speaking about simulation of fermions when we incorporate spin. So this is work from this archive here that I did with Jed. I think he's here today. So yeah, I work for Quantinuum. We're a full-stack ion trap quantum computing company. Roughly speaking, the hardware is built in Colorado and the quantum software is built here in Cambridge. Okay. So some of the introductions for what we want to exploit kind of symmetries in quantum mechanics in order to handle the spin. And symmetries in quantum mechanics, this really means representation theory. So we know, obviously, particles are in an n-dimensional Hilbert space, kind of rotating around this vector space. And then we do want to do unitary evolution on these matrices with just an arbitrary matrix. And in the presence of symmetry, we can end up block diagonalizing into the various irreducible representations. So it's very advantageous to kind of try to exploit these smaller subspaces in quantum computing. We heard this from Toby's talk. Because essentially, if you can handle a small vector space, your quantum algorithm theory should be a lot cheaper. Okay, so there's one of the famous symmetries for fermions, and in my case, I'm interested in electrons. This is the SU2 spin symmetry. So SU2 is a global spin symmetry. It's first observed by the Stern-Galak experiment, whereas a spherically symmetric 5s silver ion was shot through a magnetic field. Due to the spherical symmetry, this shouldn't have split, but it was quantized under this spooky angular momentum, which they ended up calling spin. And the dynamics of this system is governed by special unitary matrices of dimension 2. Electrons also have this famous anti-symmetry property. And the combination of SU2 and anti-symmetry leads to the Pauli exclusion principle, where no two fermions can have the same quantum number. So most of the time, when we do quantum algorithms for the fermions, we tend to just work in the spin orbital basis. But really, for quantum chemistry, we need to be working in the spatial orbital basis, where we correctly treat the total spin angular momentum. So the spatial orbitals are really, in this case, you can think of them as the atomic orbitals, but it doesn't matter. It can be any orbital basis. And we can group them under this D index. So we have basically each spatial orbital can be unoccupied. You can have a single electron up, a single electron down, or it can be doubly occupied. So often many of the electronic systems that we're interested in, particularly for quantum advantage, are these high-spin, open-shell transition metals. And we know for classical chemistry that if we don't correctly treat the spin, we'll get spin contamination. So we need to have correct resolution of the total spin angular momentum. In order to do that, you really have to incorporate the spin coupling correctly. However, this is kind of like, it introduces a very large implementation overhead, and it's not really been treated formally in quantum algorithms. So we've kind of done some work to kind of hopefully give a framework to do that. Okay, so the kind of, I would say the gold standard of, so I come from a quantum chemistry background, and the gold standard of treating spin in quantum chemistry is this unitary group approach. And this way, basically, you take the electronic interaction Hamiltonian where we have our one-body terms and our two-body terms, and these interaction Hamiltonian terms can be expressed as the generators of the unitary group, but really they're just a spin-traced fermionic operator pair of creation and annihilation operators. And we know that this Hamiltonian is spanned by this very special spin-adapted Slater-determinant configuration. So this is just an occupation of the wave function with the correct spin coupling. And then the basis which spans this spin symmetric Hamiltonian has good n, s, and m quantum numbers. And what's very nice is that there's a very deep mathematical physics interpretation of this, and that the indexing of these basis functions can be represented via a very famous Bratelli diagram, which is kind of known as the Chevit graph in the literature. So this kind of comes from, obviously it goes very far back in terms of mathematical physics. So obviously anything about mathematical physics comes from Hermann Weyl and Wigner. And then in the 70s, this was brought to kind of the quantum chemistry via Joe Paldus. And this is wrapped into like a nice graphical framework via Chevit. Mike Robb and others in the 80s, when classical computers weren't very good, were really leveraging the power of these symmetries to improve the analytical methods. He was my PhD supervisor, and he's still going at Imperial now, about 80. And there's been some modern use in this for things such as Monte Carlo approaches, like Ali Alavi is actually here in the chemistry department as well. Okay, so what we're really trying to do is trying to add a quantum algorithm to the bullet point here at the bottom. Okay. So, in order to correctly frame spin in a fermionic Fock space, we had to come up with this new duality called Powder's duality, which is where we have this decomposition of the full fermionic Fock space under UD, which is the spatial dimension and spin. So there's one prerequisite that we need for this talk is really that the characters of the unitary group can be represented via the Shor polynomials, and the characters are just the trace of the representation matrix of which the unitary representations act. Normally I have to apologize for this in most talks, but as this is the Mathematical Institute, hopefully everyone understands this already. And these Shor polynomials can be constructed with what are known as a semi-standard Young tableau. Okay, so in this example, the irreps of UN can be indexed via these partitions, and then in this example we have a UN equals 3. That means we have 3 variables in our polynomial. We basically fill up these Young diagrams which index the irrep via all possible ways where we weakly increase across the rows and strictly decrease down the rows. And this gives us a polynomial where each of the monomials represents one of these Young diagrams. And this is spherically symmetric under the exchange of variables. So yeah. So I think the main takeaway here is that your Young diagrams really index the irreps, and these are then used to build your characters of the representation. Okay. So the full fermionic Fock space, from a mathematical perspective, is really an exterior product. So and the exterior product is really, it's a graded object. So each is essentially a direct sum over these k-particle wedge products of these n-dimensional Hilbert spaces, where the wedge product is just the antisymmetric tensor product here, where we have the sign of the permutation. And the dimension of this, and then each one of these Hilbert spaces carries an n-dimensional representation, right? Because every Hilbert space can be rotated via a unitary matrix of n by n. And the dimension of these graded subspaces really is related to these Shor polynomials. And you end up with these, in this case, you end up with these n choose k dimensional subspaces within the full fermionic Fock space. Okay. Now, this is obviously for spinless fermions. But really what this is showing is that the character of each one of these antisymmetric k-particle subspaces is really what's known as what is given as it's given as one of these, because this is an antisymmetric representation, it's given as these vertical short polynomials, which are these very special short polynomials called the elementary symmetric polynomials, which are essentially just all the vertical polynomials. And the character of each one of these green subspaces is given by this this EK, which is just all possible ways of filling the vertical Young diagrams. Okay. Now, if we combine these and sum over the full trace of the full fermionic Fock space, we get the character of the full fermionic Fock space. So we have a sum now over the elementary symmetric polynomials, and this becomes this extremely powerful identity from symmetric polynomial theory called the generating function of the elementary symmetric polynomials. Okay. So this is a tool that we'll use now to decompose that this Fock space under the spin. Okay. So we know from the Pauli exclusion principle that electrons don't live in a spin orbital space. They really live in a spatial orbital space crossed by a two-dimensional spin space. So it's a tensor product Hilbert space. When we substitute this into the generating function of the elementary symmetric polynomials, we end up with this very powerful identity called the dual Cauchy identity. So we've just substituted in this dual representation now into the previous equation. And this decomposes as the dual Cauchy identity. And this goes all the way back to Newton. So we have these d variables for the orbital part, and these y variables for the x variables for the orbital part, and the y variables for the spin part. And this decomposes under this dual Cauchy identity into this product of conjugate Shor polynomials. Okay, so these are represented via these conjugate Young diagrams. So this is the d part, the orbital part can have at most d rows, and the spin part is governed by at most 2 rows. Okay. So, yeah, so this really gives you the full decomposition of the full Fermionic Fock space, because these are the characters of the product of representations, and the characters for your homomorphism give you the representations, the irreps. So what this gives you is the full Pauli duality, which I'll talk about in a second. But really, we need to just describe this an indexing convention that we now use. So we have this conjugate pair for every element of the polynomial, and here we have obviously. So we just take this in this d equals 4, n equals 6 case. We just look at the orbital part here, this vertical one. We can see that this is a partition of at most 2 columns, where we have 2 rows, 1 row, 1 row. And we can represent this as a 2, 2, 1, 1 partition. And then if we let the number of 2 partitions equal A, the number of 1 partitions equal B, and then the number of empty partitions equal C, we can reindex this as ABC, 2, 2, 0. Okay, and there's a subtlety here. So I've been talking about SU2 and U2, and these Shor polynomials really index the characters of U2, but because SU2 is a subgroup of U2, representation theory can be is equivalent. So this automatically gives us SU2 as well. So this part on the end gives you the spin irrep for this conjugate pair, and this is basically comes from subtracting the 2 partitions here, and then you can see that this gives you an S equal 1 irrep. Okay, but because of this conjugation, the ABC values simultaneously index the orbital and the spin part. So from now on, we just use this orbital part here. Yeah, so this is what I was going to say. And then simultaneously, this also indexes this total split particle number and the spin as well. So these are kind of used interchangeably. Okay. So formally, what does this look like? So we've shown that the decomposition of the full Fermionic, the character of the full Fermionic Fock space decomposes under this Pauli duality, dual Cauchy identity. And then in the full representation picture, this is what it looks like. So we have obviously a UD dimensional irrep, and the multiplicity of that space is given by the SU2 part here. So if we look at a full example of the full Fermionic Fock space for 3 spatial orbitals, 3 spatial orbitals can be occupied in 6 different ways, so 7 different ways with an empty 1, 2, 3, 4, 5, 6 particles. So you can see here that we have a 0 particle, 1 particle, 2 particle, 3 particle, 4 particle, 5 particle, 6 particle space. And then within that, we have the spin multiplicity, the spin sort of spaces. And then within that, we have the spin multiplicities of that as well. Okay, and we show that this can be decomposed with the identities of the symmetric polynomials. So we just have a concrete example of this. Taking this n equals 3 case, we can see that the dimension of the block is given by the dimension of each block is given by the Shor polynomials we showed before, and the multiplicity of this space is given by the U2 part. So now this one we're filling it with 3 numbers, and this one we're filling it with 2 numbers. And these are conjugate, they're reflections of each other because they're conjugate. And simultaneously, the U2 simultaneously indexes the SU2 spin part as well. So this is just showing that the SU2 and U can be both represented via SU2 and U2 can be both represented by the semi-standard Young tableau. Okay, so hopefully I convinced you now that we've rigorously decomposed the full fermionic Fock space, and I think that we were the first people to do this, at least. And what's very nice now, which is something that's very emergent out of this, is if you look within the dual couch identity up here, so this is the D level one, there's a polynomial recursion within that. So if you see here, at the D-1 case, we also have a dual couch identity. And if we multiply this out, we see that to go from here to here, you have this 4-term polynomial. And this is kind of the branching recursion, which leads to an internal structure of the wave function. Okay, and we went through a lot of effort to prove this. So if you look in the appendix of our paper, you can do it all with character theory. But what this leads to is this Bratelli diagram, this kind of restricted Bratelli diagram of these 2-column Young diagrams, which give you the internal recursion of the irreps for each spatial orbital level. And there's 4 different branching strategies between each node, okay, in the Bratelli diagram. So you can see basically the 4 cases are, you can either increase, you can couple an empty spatial orbital, you can couple a 1-spin orbital, a spatial orbital with 1 spin with a +1/2, couple a single electron spatial orbital with a total spin -1/2, and then you can also couple a doubly occupied spatial orbital which has a total spin of 0 because it's spin paired. So you get this. At each orbital level, you get these 4 different branching recursions that you can get, and this gives us amazing internal structure of the full fermionic Fock space. Okay, when you account for the spin. All right, and then this is also within this structure. Essentially, it's the Gelfand-Zeppelin basis for those who are familiar to the representation theory of the Uchi group. Okay, so now. We've shown that the vector space can be deconstructed in this way, but how do we build the representations? And the classic way of building representation at SU2 is using Clebsch-Gordon coupling. Okay, so this is a recursive construction where you spin couple, depending on your internal spin projection and total spin, a coefficient, which then gives you a basis, a spin-adapted basis coefficient. That's what this is up here. So basically, each one of these walks on this node is a spin products to a spin-adapted coefficient, and then this is the SU2 part, and this is the UD part here. So basically, the branching on the UD graph gives you the internal Clebsch-Gordon coupling along that path. So each one of these paths couples a whole set of Clebsch-Gordon coupling, basically. So this left-hand side is basically N, S, and M. N and S, sorry, and then this is the M part. Okay. So you can kind of think about this indexes, each D is a path to this node, N and S, and then this side is this SU2 coupling. Okay, so this can actually be wrapped up very neatly within a spin network of Clebsch-Gordon tensors, where the elements of this spin coupling graph on this side are kind of wrapped up as the tensor elements of this network. And yeah, it basically leads to a very nice kind of construction of the spin coupling. Okay. So you can see there's a few different walks along the Chevit graph of this UD equals 3 example, and you end up with, for each pathway that you take on this graph, you end up with a unique spin coupling. Okay, which is very cool. Now, the aim of the game for a quantum algorithm is to do this in superposition, right? So we want to be able to in superposition encode take in a full fermionic wave function in the occupation number representation, and simultaneously branch along this graph and map it into this spin-adapted representation. Okay, so that's the game. So we were very fortunate that we could see that if you looked at the Clebsch-Gordon coefficients for each of the branches from a single node, so each node here goes from n and s, and then we have the 4 possible branches from the Chebyshev graph, which couple an empty orbital, couple 1 electron in a spatial orbital, plus a half, minus a half, and a doubly occupied one, which adds a particle number of 2, but doesn't add an overall spin. Obviously, only the singly paired electrons add a total spin coupling, because you have the other 2 are doubly occupied and empty. And these have this very nice trigonometric identity where they could be wrapped up in terms of a Gibbons rotation, which is a special gate which is used a lot in quantum computing. So this is really the moment where we realized we could construct this in a quantum algorithm. And we call this kind of extended genealogical coupling. And this is really based on a lot of the work from this paper in the 1980s, actually. Okay, so we now obviously built this construction. How do we build a quantum algorithm for that? And we call this the quantum powers transform, which takes a occupation number fermionic wave function and takes it into the spin-adapted UD cross SU2 wave function. So we base this construction using this iterative algorithm. It's based on an algorithm called the Shor transform from Dave Baker, Aram Harrow in 2006. Whereas we take it, you can see we take in a paired spatial orbital, and then we apply the Gibbons rotation, and we branch along the graph. So I'll go through these components individually. So we basically have this kind of this generalized Clebsch-Gordon transform, where it's generalized because we're coupling orbitals as well as spins here, so we're adding particles as well. And if you want to do graph traversal in a quantum algorithm, kind of the way to do that is a controlled incrementation. Okay, so this is a kind of controlled incrementer. So an incrementer is just cycling you around mod n within your qubit basis. So you can see here, if this is 1, then this 100 will then get incremented to 101, which is just plus 1. And there's an efficient compilation for this. So the incrementation for the n case is slightly more complicated because we have basically, depending on if we're going on the 0, 1, 2, or 3 branch, we need to increment n by either 0, n plus 1, or n plus 2. You can see this is quite straightforward. We just apply a double incrementer controlled on the various incoming. And the truth table is given here. The spin case is similar, but the incrementation is slightly different because here we need to go either spin plus 0, spin plus half, spin minus a half, and spin plus 0. And we can do that again via a very similar construction where we have a plus a half incrementer and a minus a half incrementer, where I've just this is just the spin mapping. So this is a plus 1 in binary and plus minus half in binary. So yeah, and then the M graph is the same. And then the most expensive part of the algorithm is really the controlled Gibbons rotation here, which is a multi-controlled set of Gibbons rotations indexed on the spin and the M value. And depending on the spin coupling that you have, the Gibbons rotation will increment the various rotation of that spin coupling for the S and M. And this is really the main cost of the algorithm here, because you have this very complicated multi-controlled rotation here, which is typically something you want to avoid in a quantum algorithm. However, we were able to compile this with some clever QROM constructions, and this has a Toffoli complexity of d squared. But if you do some clever tricks and you flatten all of the S and M indices into a single vector, you can basically push the complexity almost down to linear, I would say. So even for a 50 spatial orbital problem, d equals 50 here, which is in the regime of quantum advantage for most chemistry applications, this is about 5,000 Toffolis, which is probably, I would say, it's a negligible cost compared to a lot of these very expensive phase estimation block encoding algorithms. Okay, so I've got 5 minutes, so I'll briefly touch on. So we've come up with this mapping. Now, we want to do computation in this basis. We want to exploit Hamiltonians in this spin-adapted basis. And to employ quantum linear algebra type operations, you need to do block encoding. Okay, so we want to take our Hamiltonian, which is the spin-adapted unitary group Hamiltonian, and encode this in a larger unitary by this method called linear combination of unitaries. So the matrix elements are obviously going to take the form of this, which is obviously the unitary group Hamiltonian. And the EIJs, these individual parts, they actually have this very neat graphical interpretation, okay, where the actual matrix elements of this wave function in the spin-adapted basis actually have these forms of overlapping walks, where whether the walk is allowed is given by the underlying spin coupling. Okay, yeah. So in order to do this, essentially what you do is you take the Powers transform, and then you can recast it as an MPS type construction where you can see quite naturally that this spin coupling can be recast as an MPS, where for a given incoming D value, you will get a different MPS construction. So we can basically map from the spin-adapted basis, and then basically what happens is once we take the matrix elements, because each walk on the UD part carries the Clebsch-Gordon coupling, what basically happens is you end up with this decomposition under the SU2 rack 6J symbols of angular momentum coupling, which basically, what I'm saying is your matrix elements basically decompose under this algebraic tensor network of rack 6J symbols, which is very cool. Okay. So this is still work in progress, but this is all derived in these papers in the 80s. So to do this on a quantum computer, it's straightforward. You just apply the quantum Powers transform. You then do the fermionic block encoding operation, and then you map back out the Powers transform, and then trace out here. And this gives you the matrix element. And we basically, the overall cost of the algorithm is essentially d squared plus d. So the Powers transform is d squared, and then we have a fermionic block encoding that has cost d. And we can do this. I can't go into detail about that, but if you ask me later, I'll be able to tell you. Okay. So then the block encoding construction takes this LCU form. So if we just concentrate on this very complicated Coulombic term here, which is a rank 4 tensor, we can take this rank 4 interaction tensor and decompose it under a higher order SVD. And then that allows us to directly work in the directly construct a block encoding for this, which implements the Powers transform, the fermionic operations in superposition, and then the weighting of each of those fermionic terms as well. And then this applies the operator term. Yeah. Okay. So the overall cost of this is d squared as well, which is very nice. So remember, this is in the spatial orbitals as well, so we actually get a factor of 2 improvement over the spin orbitals. Okay. All right, so in conclusion, we essentially developed a rigorous framework to decompose the full fermionic Fock space under these global symmetries. We implemented a new quantum algorithm to leverage Clebsch-Gordon coupling to build this symmetry-adapted state. And then we've come up with a block encoding to work with this spin-coupled basis. Okay. And I think this is completely generalizable to other fermionic problems, particularly SU3, etc. I would find some future direction. I think we want to kind of incorporate some of these double factorization and tensor hypercontraction approaches to drive the method to linear scaling for the block encoding. Okay. So yeah, and just a final point, we really need to be able to deal with spin correctly to get these molecules which really the candidates of quantum advantage. So yeah, I think we will need all of these approaches for that. All right, thank you.
The questions from the audience? Comments? Let's see. Maybe naive questions. We talk about something which is proof of concept, or you can see a hardware implementation?
Yeah, I mean, so my other job, other than this research, is to implement all this stuff into our quantum software library for quantum algorithms. So it's on my to-do list. But there's lots of, I would say that all of the components of the algorithm we have, just need to, like, the QROM, etc. Like, we have most of the components. So, like, but I would say we haven't implemented at algorithmic level, but we haven't implemented them on hardware yet.
So you also have not thought about breaking of the symmetry, which is how, so, because probably noise and this.
Yes, yeah, it's very true. I mean, like, when you have, like, noise, where you lose all this nice information of, yeah, I don't know how that would affect it. Probably not good, I imagine.
And could you generalize this to gauge symmetries? I believe your company has a collaboration with DAISY, with a high energy physicist. And I guess in that case there are other kinds of problems, but maybe...
I'm looking for collaborators in this exact area. So, yeah, SU2 is a gauge symmetry, if I'm aware. SU2 is a gauge symmetry. So I think you should probably generalize it to other things.
Yes, that's probably another kind of business.
All the polynomial identities are generalizable to things beyond SU2, like SU3 and SUN.
So then there's room.
Yeah, for sure. As long as it's fermionic.
Yeah. Well, fermions are very interesting also in energy physics. So.
Yeah. I mean, this dual Cauchy identity as well. It has an equivalent formulation in the symmetric subspace, so it would work for bosons too. I'm just not interested in that because I'm a chemist. So, like, if you see, this guy. So, yeah, there's an equivalent. So this is the dual Cauchy identity, but the Cauchy identity is this, but for a symmetric. So you just have a symmetric product rather than the exterior product here. So imagine there'd be a boson formulation of this too. You'd have to truncate the basis though. Yeah.
Thanks for the comment. Yes, please.
So it's super nice maths. I'm wondering I'm a little bit confused about what the payoff is, because usually when you do this kind of global symmetries, you can do this and you reduce the Hilbert space dimension, but you pay a price. And the fact you make, I don't know the one I put up, you then make the implementing the terms of the Hamiltonian in that basis is then a hollow mess here. So you actually see actual gate count reductions or depth reductions in this, not just asymptotically concrete numbers from doing this and making use of all of this stuff.
So the one benefit I would say that you get from this is that because your Hamiltonian naturally comes as this generated product, it already, because you have this, sorry. Yeah, this guy. So yeah, because the Hamiltonian comes in this form, you already have this double factorized product for free, essentially. Okay, and then in order to be able to access this Hamiltonian, you have to do this transform. So I would argue that double factorization approach of Google, etc., you have to do a huge numerical overhead to get the Hamiltonian into that form, whereas this naturally just comes in this form if you can transform into that basis.
But that's classical overhead.
It's true, but you end up having all these Gibbons rotation on top of
in your circuit.
Yeah, in your
this
circuit.
Is true. Yes.
So there's a kind of equivalent thing.
I also a little. I mean, okay, if you're going
Block encoding, it's sort of swallowed up in all the other massive constants anyway. So if you actually, I'm a little bit skeptical about the double factorization as well for that reason exactly.
Yeah.
So you're looking in the asymptotic scaling setting when you're going to do block encoding, where do you have concrete numbers of whether it outperforms the?
Not yet, but because we have the spatial, we're working with spatial orbitals. You would have a factor of 2 overhead over the spin orbital complexity. But yeah, this is to be investigated, I would say. The other thing that I would say is that it's not just the asymptotics, it's like you unveil this like beautiful algebraic structure within the wave function, which could be a tool. I think there's targets. Like if you think about this, each element of the Hamiltonian term here is now factorized into this RAC6J angular momentum coupling. And there's much less of these than matrix elements. So I think there's a deeper structure to be investigated here from a quantum physics perspective.
Super beautiful. I won't ask you what the Quantinuum manages.
Yeah, so this is why I built the block encoding library, so it's my insurance policy to do this interesting research.
So let's thank the speaker again.